Hello everyone, welcome to the second part of first tutorial. So, we will start with question 8. So, in question 8 we are defining a functionally complete set of logical operators. So, if you are given a set of logical operators, we say it is functionally complete if every compound proposition can be converted into a logically equivalent proposition involving only the logical operators that is given in your collection. Okay. So, the first part of question 8 asks you to the following. So, here we want to prove that the set of these 3 operator is functionally complete. That means, any compound proposition you can represent just by using these 3 operators. Okay. So, how do we prove this? Well, if I am given a proposition which indeed involves only these 3 operators, I do not have to do anything. But what about a compound proposition where I have an occurrence of implication? In that case, what I can do is I can use this logical identity that P implies Q is logically equivalent to negation of P disjunction Q, and I can substitute P implies Q by this RHS expression, and by applying this rule repeatedly wherever I have an occurrence of implication, I can remove those implications and I will be now have an equivalent formula where everything is represented only in terms of conjunction, disjunction and negation. What if my expression has by implication symbol? I do not have to worry. What I have to do is I can use the identity that the by implication is nothing but conjunction of 2 individual implications, and I know that each individual implication can be replaced by these 2 sub expressions. So, now you can see that my original expression is converted into an expression where every operator is either conjunction, disjunction and negation. So, that shows that if you have these 3 operators, namely a conjunction, disjunction and negation, you can represent any statement, any compound proposition, and hence this is a functionally complete set of logical operators. Now, the second part of the question says that I do not need both conjunction and disjunction to be there. It is sufficient if I just have a disjunction and negation operator and I can represent every statement. Okay. So, what I have to do is, from the first part of the question, I know that if you have an occurrence of implication, you can represent them by just using negation and disjunction, right. This is what we have shown. What we have to now worry about is how do I represent even a conjunction, namely a proposition where conjunction is involved by an equivalent proposition where I have just occurrences of disjunction and negation, and this is how we can prove that. Imagine you have an expression of the form conjunction of P and Q. This is logically equivalent to negation of P, conjunction negation of Q, and then by De Morgan's law this is nothing but equivalent to negation of this entire expression, namely disjunction of negation P and negation Q. So, now you see that even if you have an occurrence of AND in your expression, you can substitute that expression by another expression where you have only occurrences of negation and disjunction, and which shows that just your negation operator and disjunction operator are functionally complete. You can represent any statement. Okay. The third part now says that you have to show that only the negation operator and the conjunction operator, they are functionally complete, and here we have to show how we can represent a disjunction in terms of conjunction and negation. And again we have to do similar thing which we have done for the previous part. I can represent any disjunction in this form where I have just occurrences of negations and conjunction. Okay. So, that shows that just 2 operators, either conjunction along with a negation or a disjunction along with negation, is sufficient to represent any expression that you are interested in. Now, question 9 ask you to show whether this long expression, long compound proposition is satisfiable or not. So, what I do here, this expression is already in its conjunctive normal form, and what I have done here is I have written down the various clauses that are involved in this compound proposition, and I have to worry and I have to think that how is it possible that I can simultaneously satisfy all these 6 clauses. Well, if this expression is satisfiable, then there might be many truth assignment which can satisfy all these 6 clauses. Our goal will be to find at least one of them. So, let us try to do that. So, what I do here is, if I ensure that R is true, then that will ensure that my clause C1 will be true. I do not worry what is P and Q. If I ensure R is true, the disjunction of R with everything will be overall true. And if I assume R to be true, okay, what happens here is, if I go to clause number 4 here, if R is true, then negation of R will be false, right. Negation of R will be false. Then what I have to do is, in order to satisfy clause number 4, I have to make negation of P to be true or negation of S to be true. So, let me make negation of P to be true. For that I have to ensure that P is false, because if I ensure P is false, negation of P will become true, then overall this expression C4 will become true. That is why I have put tick mark here, that means this clause will be satisfied now, and due to the same truth assignment P equal to false, the clause C2 also will be satisfied, because I have an occurrence of negation P. That means, with R equal to true and P equal to false, I will be able to satisfy clause number C1, clause number C2, clause number C4. Okay. Now, my negation of R will be false, because I am assuming here R is true, and I am assuming P to be false. Then, to satisfy clause number 6, I am left with only one option, namely I have to ensure negation of S is false, then only clause 6 can be satisfied, and negation of S is false means S sorry. So, okay, so what I am doing here is, I am not trying to satisfy clause 6 as of now, I am trying to satisfy clause number C3 first. And to satisfy clause number C3, what I observe here is that P is already taking the value false here, okay, and Q is not taking any value as of now. I have not assigned any value to the Q, okay. But what I observe here is that if I ensure that negation of S is true, then clause C3 will be satisfied, okay, and negation of S is true means S is false. And if I ensure S is false, my clause 6 also gets satisfied, because I have an occurrence of negation S. I do not have to worry what is P and negation R at the moment. That means, now assigning these values to R, P and S, I am able to satisfy all the clauses except clause C5. Clause C5 is not yet satisfied, because I have assigned P to be false and I have assigned R to be true, so negation of R is also false. So, the only way I can satisfy clause number 5 is I give the value true to clause number C5, and that means I have found at least one truth assignment which can satisfy all these 6 clauses. So, now you can see that if your expression is in its conjunctive normal form, you can run this, do this mental algorithm. You can try to individually satisfy each clause at a time and try to come up with a truth assignment which can satisfy all the clauses. Okay. So, in question 9a there are some other expressions also which are given to you, and you have to verify whether they are satisfiable or not. I am leaving that for you. So, let me go to, sorry, this is not 9b, this is question number 9 a dot 3, sorry for this numbering. So, the question basically asks you to show the following. It says that imagine you are given an algorithm which can check whether a compound proposition is satisfiable or not. You do not have to worry about the details of that algorithm. Imagine that is a box given to you. You feed some compound proposition to that box and it gives you an yes no answer. Now, using that algorithm, that box, you have to come up with another algorithm which should tell you whether any input that you feed to that algorithm is a tautology or not. Okay. So, we first prove a very simple fact here regarding satisfiable statements and tautology. The claim here is that if you are given a compound proposition x, then it is a tautology if and only if negation of x is unsatisfiable, and it is very simple. Okay. And this is an if and only if statement. So, let me prove it. If x is a tautology, that means it is always true. Then what about the negation of x? The negation of x can never be satisfied. You can never find a truth assignment which will make negation of s true, because if negation of s is also true and x is also tautology, then that is not possible simultaneously. Okay. On the other way around, on the other hand you assume that if negation of x is unsatisfiable, then I have to prove that x is a tautology. We prove it by contrapositive. So, showing that negation of x is unsatisfiable implies x is tautology is equivalent to showing that if x is not a tautology, then negation of x is satisfiable, right. Our goal is to show p implies q, and this is equivalent to showing negation of q implies negation p. So, if I want to show p implies q, it is equivalent to, if it is enough if I show negation of q implies negation of p. And what is negation of q? Negation of q is x is not a tautology, and what is negation of p? That negation of x is satisfiable. And indeed, this implication that if x is not a tautology, then negation of x is satisfiable is a true implication, because if x is not a tautology, that means it is not the case that x is always true. That means there is one truth assignment for which x is false. For that specific truth assignment, what about negation of x? For that specific truth assignment, negation of x will be true, because for that assignment x was false, right. So, that proves the implication of this theorem statement in the other direction as well, and that is why this is a condition. So, now we can utilize this theorem to get an answer for our question. So, as I said earlier, you are given an algorithm, I call that algorithm as ASAT, which takes a compound proposition and it gives you a yes no answer. It gives you an answer 1 if x is satisfiable, it gives you the answer 0 if x is not satisfiable. Using this, I designed another algorithm which I call as algorithm tautology, which will take some compound proposition and it will give me an answer yes if x is a tautology, otherwise it will give me an answer no if x is not a tautology. And I am allowed to use this existing algorithm ASAT. What I am going to do is, my algorithm a tautology will do the following. It will first find a negation of my input x. So, I call that expression as y, and I give the compound proposition y as an input to my algorithm ASAT. The algorithm ASAT will give me a yes no answer. Okay. It will give me the answer 1 if y is satisfiable, it will give me the answer 0 if y is not satisfiable. What I have to do is, I have to use this response that I am getting from algorithm ASAT to decide the outcome of algorithm A tau. And my output is the following. If my ASAT says that y is satisfiable, I will say that x is not a tautology. Whereas, if ASAT says that y is not satisfiable, I will say x is a tautology. That means, I will just give the reverse answer, opposite answer which I got with respect to the expression y from the algorithm ASAT. And this is because of the following theorems, this is because of the theorem statement which we have just proved now, we have proved that if at all x was a tautology, then y will be unsatisfiable, right. That is why I am just flipping or complementing the bit or the response which I am getting for the expression negation x from the ASAT algorithm. What will be the running time of the algorithm A tau? The running time will be almost the same as your algorithm ASAT plus the running time that you need to convert your expression x into expression y. Okay. That means, if your algorithm A tau is going to say take 1 hour and converting expression x to expression y takes say 10 minutes, then the running time of A tau will be 1 hour 10 minutes. Okay. It will be almost proportional to the running time of ASAT. Okay. In question 10, you are given a set of premises and a conclusion, and you have to verify whether this is a valid argument or not. So, what we first do is we convert statements into propositions. So, I introduce the variable p here, and this is a simple proposition. Then the second statement, to represent that I introduce another variable q, because Randy works hard is already represented by p, and the second statement will be represented by then p implies q. For the third statement, I need another variable r here to represent that Randy will not get the job, and then the third premise is q implies r. The conclusion that I am drawing is Randy will not get the job. The argument form here is very simple. You are given 3 premises and the conclusion is r. Let us see whether this argument form is valid or not. So, what I do is I apply modus ponens on the first 2 statements here, the first 2 premises here, and come to the conclusion q, and then I apply again modus ponens on q and the third premise and draw the conclusion r. That means, this is a valid argument form, a valid conclusion, because I can draw the conclusion from my premises. Okay. Now, in question 11, you are given the following. You are given that this argument form is valid, where you are given a set of n premises and the n plus 1th premise is q and the conclusion is r. Now, you have to show, if this is the case, then the argument form where only p1 to pn are the premises and the conclusion is q implies r is also valid. Again, there are several ways to do this. You can use truth table argument and so on, we will avoid that. Since we are given that this argument form is valid as per the definition of valid argument, I can say that the conjunction of p1 to pn and q implies r is a tautology. Okay. That means, it is never possible that your left hand side is true and RHS is false, that is not going to happen. That means, if my LHS is true, RHS is also true. That means, if the conjunction of p1 to pn and q is true, then r is also true, and as a result I can say that this implication is also true, because if the conjunction of p1 to pn and q is true, that means this part is definitely true, this conjunction of p1 to pn is true, right. And since q is true here, r is also true, then true implies true is anyhow true and true implies true is anyhow true. Okay. But if I closely see here, what does exactly this implication means? If I say that this implication is always true, then another form of this implication is that you have the premises p1 to pn and the conclusion is q implies r. And if I want to say that this argument form is valid, this is equivalent to asking whether the conjunction of p1 to pn implies q implies r is tautology, and that is what we have proved here. That means, if this is given, if this argument form is given to be a valid argument form, then this new argument form is also valid. Now, let me go to question 12. I will not be solving the part A here, I will be focusing on part B. Part A I am leaving for you. You have to show using resolution whether the following argument is valid. So, these are the premises here, these are the 3 premises and this is the conclusion. Okay. So, as usual the first thing that we will do is we will introduce propositional variables and bring everything in the form of compound propositions. So, if I introduce the variables here like this, okay, it is up to you what form of the variable you use. I am using it is not raining as negation of R. You could have used R to denote it is not raining. Okay. In that case it is raining becomes negation of R and so on, and you can use any name. You can use A, B, C for propositional variables, just for my convenience that I am using these names. Now, if I use these propositional variables, then the argument form here is the following, and I have to show whether this argument form is valid or not. The first thing I have to check is whether this argument form is in its clausal form or not. That means everything, the premises and the conclusion, everything is in the form of clauses or not, and in this case yes, this is clause C1, this is clause C2, this is clause C3 and this is clause C4. What is the resolution refutation method? The resolution refutation method says that you take the set of clauses which are your premises and to that you add the negation of your conclusion, right. Remember, we have to check whether S union negation of the conclusion, if the resolvent of this thing is false or not. If that is the case, then I say that C is a logical conclusion from my set of premises in the set S. That is what is the proof by resolution refutation. So, I have added the negation of the conclusion. And now I have to resolve. So, I take the first 2 clauses here, I cancel out U here and I get the resolvent disjunction of negation R and negation W. Then I choose the resolvent and the next clause here and I cancel out R and R here and I get negation of W, and now if I take negation of W and W I cancel them and get false. Okay. So, since I am getting the resolvent to be empty, that means this is a valid argument. Okay. So, now let us next go to question number 13, and in question number 13 we have to use resolution to show that the following compound proposition is not satisfiable. Okay. And as per the properties of resolution, basically to show that the conjunction of these clauses is unsatisfiable, I have to show that the constant f belongs to the resolvent of the above clauses. So, let us build a resolvent or resolution tree for this set of clauses here. Okay. So, I can pick the first 2 clauses and resolve P, and then I can pick the next 2 clauses, the last 2 clauses, and I can again resolve P. So, the resolvents are now added to the tree, and now I can pick these 2 resolvents for resolving and I obtain the conclusion f, the constant f, which shows that the conjunction of these 4 clauses is not satisfiable. Okay. So, that is how you can actually prove whether a compound proposition is satisfiable or not. You have to bring everything in the clause form and then build a resolvent resolution tree and then arrive at the constant f. Now, let us go to the last question for the first tutorial. Okay. So, again you are given a set of English statements in, and you have to verify whether that is a valid argument or not. So, what I do here is, as I am repeatedly doing it, I will be introducing propositional variables and converting each statement into some compound proposition. Okay. You are free to use any variable name here. I am just using these variables for my convenience. So, after converting everything, this is the argument form here. Okay. And I am going to use proof by resolution refutation, because I find it very comfortable, because you just have to keep on cancelling clauses here, right, cancelling literals in two clauses and keep on doing the simplification till you either get empty conclusion or you can't resolve further, right. You do not have to worry about logical identities, De Morgan's law, etc., etc. That is why resolution refutation is a very, very powerful proof mechanism. So, these are your set of premises converted into their clauses, equivalent clauses, okay, right. So, in this case I have to convert some of the premises into their corresponding clause form or CNF form. In fact, I have to convert everything, because not all the clauses, not all the premises are, none of the premises are available in their CNF form except this negation P. Negation P is available in its CNF form, everything else have to be converted. After converting, I have added all the premises. So, that is my set of clauses or premises S. And what is the conclusion? Well, the conclusion that I am trying to draw is negation of E, which is already in its CNF form, but I have to add the negation of C in the resolution tree to do the resolution refutation proof mechanism. And now I have to resolve. So, I start with first two things, cancel out P, and then I cancel out A, I then cancel out W, I then cancel out I, next I cancel out M, and then after cancelling out E, I am left with nothing, empty. So, I got the resolvent to be empty, and that shows that this is a valid argument. Well, you could have showed that this argument form is valid by using simplification, rules of inferences, modus ponens, etc., etc. I am not stressing that you have to only use resolution refutation, just that I find a resolution refutation to be a simpler proof mechanism. And again, the tree that I have constructed here need not be the only tree when you are building the resolution, when you are doing the resolution refutation proof. You might pick the pair of clauses to resolve in any arbitrary order. It is just that some trees lead you to the empty conclusion very soon, some trees might lead you to the empty conclusion after a long time. So, depending upon which two clauses you cleverly use at each stage, that will determine how fast you reach to the empty conclusion, that is all. Okay. So, with that I conclude the first tutorial. Thank you.